Okay. What I mean by source inductance, suppose you have a generator which is stepped up by some type of transformer, then you have a transmission line, three-phase transmission line, and then you will have a couple of step down transformer, and then finally it will be connected to the load. So we consider the generator as well as the transformer, their inductance value is much higher as compared to the resistance of each phase. So basically, what we can think of that suppose you the winding there should be RS and LS, that is the winning resistance, generator winning resistance, and generator winning reactance. And then for the transformer, we can think of another uh, reactance or inductance, that is the LTS, and then the reactance of the transmission line. So if you combine them together, then you will find there is inductance that will be in between the load and the source. So before, when we were discussing about the half wave rectifier or the full wave rectifier, we didn't consider the source inductance. Uh, so now we will try to rethink how this source inductance might change the waveform, the output waveform, whenever you have a half wave rectifier or full wave rectifier. So, firstly, let me consider a half wave rectifier circuit. So, suppose you have a ideal half wave rectifier circuit, you have a source, and then it is connected to a diode D1. And then we can think of a basic DC current source. So how we can have a constant DC current source? In the last class, we said how we can have a constant current here. Can anybody tell? When we have highly inductive load, right? So suppose this is our circuit, and we have a half wave rectifier circuit with a constant current that is being drawn by a highly inductive load. So now, if we consider that this is our input voltage waveform, something like that. This is my omega t, and this is my V input, V in. So during the positive half cycle, what will happen? For the positive half cycle, as you can see here, this is my omega t. And if I want to have this output voltage V naught, so during the positive half cycle, the voltage polarities will be like this, and then the diode D1. Can you tell me whether it will be in forward bias or reverse bias? It will be in forward bias, right?
Yes.
And current will tend to go in that direction. And when the diode is forward bias, meaning the diode will work as a short circuit path. So whatever you have the input voltage, it will appear across the output, right? So it will be your input output voltage will be similar that you have as your input. Suppose this is my output voltage, and here D1 is conducting. Now, since it's a current source, meaning you have actually a high inductance connected to it. So what will happen if the voltage changes its polarities? So what will happen then? If the voltage changes its polarities, then the diode tends to have a reverse polarities across it, but since this inductance doesn't like the current to change its direction and the direction is in that way, so this inductance will force the diode to remain turned on. So if you have this thing configuration, then what will happen? You will find that for the negative half cycle also, the diode will still be conducting because the currents, the inductance is behaving like a current source, and this inductance doesn't allow this diode to be turned off. So if I see that your input voltage is like this, sorry, this should be negative, and your output voltage is same as the input voltage, then what will happen? What would be the average value of this output waveform?
0.
What?
0.
0. So in that case, what we can do here is that since that this inductance requires a path for the current to flow, how about between these two terminals A and B, we include a diode like this. And this diode is known as freewheeling diode. So, any question? Any question?
স্যার এই যে ফ্রি হুইলিং ডায়োডটা কেন বসাইছে আবার একটু বলবেন?
Yeah, I am explaining that right now. So, if you don't have the freewheeling diode, then what will happen? The current source, the inductance being its value very high, it will behave like a current source, and this current source will force the diode to remain turned on. And as long as the diode is turned on, then your input voltage will appear as the output voltage. So in this portion also, although the polarities will be reversed, still this reverse portion will appear across the output. So in order to avoid the, and your average value will be 0. So in order to avoid that situation, what we can do, we can introduce a freewheeling diode between the terminals A and B. So during the positive half cycle, what was my polarities? My polarities was this plus and minus, and the diode will start conducting. And as soon as that diode starts conducting, then what will happen? These polarities will make this freewheeling diode turned off. And then your input voltage will appear across the output and will have this positive half cycle. But as soon as your polarities gets changed, negative and this positive, then what will happen here? This freewheeling diode, it will start conducting, right?
Yes, sir.
So as soon as the freewheeling diode starts conducting, meaning this path will be short circuited and the inductor current, it will flow through the freewheeling diode, right?
Yes, sir.
So now if I draw the output voltage waveform, then what will be my output voltage during the time when the freewheeling diode is operating? From here to here, which diode is operating? Suppose this is DF means freewheeling diode is operating, and that instant the output it would be 0, right? And this condition will repeat itself. For the positive half cycle, you will have the input voltage similar to the output voltage, and during the negative half cycle, this freewheeling diode would operate, and your output voltage would be zero for that time. And if I consider my output current I naught to be a constant current, because we are considering this constant uh, current source. So now during the positive half cycle, this constant current, what will happen to the constant current? This constant current, it will come from the input, right? Because this diode D1, it is conducting here. So during the positive half cycle, if you consider your input current I in, your input current would be same as the output current during this portion, right? But during this portion, when the freewheeling diode is conducting, then what will be your input current?
Negative.
Zero. Zero, right? Because all the load current will follow through the freewheeling diode, leaving zero current from the input. So your input current waveform will be something like this. You understand what I am talking about, right?
স্যার
Yes.
স্যার নেগেটিভ হাফ সাইকেলে স্যার যে কনস্ট্যান্ট কারেন্ট সোর্সের জন্য ডিএফ এর মধ্যে দিয়ে তো কারেন্ট ফ্লো হবে, তো তাইলে আউটপুটে আমি একটা ভোল্টেজ পাবো না, মানে এটা জিরো কেন হবে যেহেতু কারেন্ট ফ্লো হচ্ছে, একটা ভোল্টেজ হওয়ার কথা না?
What is the diode voltage? When diode operates, no matter how bigger is the current, what is the voltage across the diode?
Voltage difference is zero as it is short circuited.
Yeah. So there would be no output voltage.
Yes, sir.
You understand my point, right?
Yes, sir. Yes, sir.
So now let us see the same circuit when we have a source inductance, because that should be the practical case, right? Here we are considering an ideal case when we are not considering any source inductance between the input and the output or the load side. Now see what happens for the same circuit when we are considering the source inductance. So now suppose we are having the same circuit, that is my V input, and then we are having a source inductance, that is LS, and then it is connected to a diode D1, and here we are also adding another freewheeling diode, that is my DF, and then it is connected to a current source, meaning this is my output V naught, meaning that there is a highly inductive load connected at the output terminal, highly inductive load. Now, if I want to have the waveform, then let me draw the waveform first. So suppose again, we are drawing the waveform for input voltage waveform. So suppose this is my input voltage waveform, something like that. So this is my input voltage waveform. And then I am just keeping this thing one cycle ahead to understand what's happening here. So this is my input voltage. So now during the positive half cycle, as you know, this diode D1, it will try to operate, right? And during the negative half cycle, which diode will try to operate?
So DF and D1.
Yes.
DF.
So now for the negative half cycle, actually this DF will try to operate. Now, since we have a inductance between the input and the output, let's see what happens. So when during the positive half cycle, when there was no inductance in the circuit, we didn't consider that, then what will happen? As soon as the voltage becomes positive, the diode, it starts operating, right?
Yes, sir.
And before that, uh, if you consider this negative portion, then what will happen? This freewheeling diode, it will try to operate and it will be operating during the negative half cycle. So as soon as the positive half cycle starts, then this D1 diode, it will turn on, and that DF diode, the current through it, it will be turned off. And that was not problematic here. As you can see, that was not problematic since we don't have a inductance here. But if you have a inductance here, then what will happen? You know the voltage across the inductance is what? L into D over by dt, right? So suddenly, if you jump from a certain value to zero, or if you jump from zero to a certain value, then what will happen to your di over dt?
It will be infinity.
It will become infinity, right?
Yes, sir.
You understand what I am trying to say, right? Any question?
Yes, sir.
Okay. So now, so the inductor, it will not allow this current to change certainly from zero to a certain positive values at once. Rather, what will try to, since you have an inductance here, and this inductance value, if it is high, then it will try to uh, keep the current linearly increasing rather than have a spike, current spike. So now, if the diode, when this positive polarity appears across the diode, and then this diode becomes short circuited, then what will happen? Suppose now we are considering this diode, this current through this diode is zero. And through the diode is zero, but the diode will have a positive polarity across it. So the diode is on, but the current cannot go through it because, like the previous case, the current cannot jump from zero to a certain value instantaneously. So if the diode becomes turned on, then what will happen? This diode is turned on for the positive half cycle since it is changing its polarities, and during the negative half cycle also, this diode, freewheeling diode, it was operating for the negative half cycle at least from up to this point. And then from negative to positive, when it is transitioning, like here, this point or this point here, when it is transitioning from freewheeling diode to the normal diode, since we don't have any inductance here, there was no problem. And the current can instantaneously change its value. But now what is happening, since you have a inductor in the circuit, then the inductor doesn't allow you to jump the current magnitude to certain value with a zero time frame. So up to a certain point, it will appear like this both diode, it will be turned on, and the current, if it is my ID current, so as you can see, during the negative half cycle, this ID current was going through this freewheeling diode. So since this inductance doesn't allow the diode to take the output current instantaneously, so the current through the diode, it will linearly increase, something like that, up to ID, and the current, the way the current will be increasing through the diode D1, the current through the diode DF will be decreasing in similar fashion, because the sum of these two currents should be equal to what? Your output current, right? Or in other way, what we can say, that your ID is the summation of your ID1 and your IDF, right? So the way your ID will be increasing, the same way IDF will be decreasing to make this current ID always constant. Do you get my point?
Yes, sir.
So now when these both diodes are operating and they are handing over the currents, then what will happen to the circuit? How the circuit will look like. So if I redraw this situation now, so you will have your V input, your source inductance, and this diode is short circuited, D1, and you have this DF also short circuited, and then you have a current source. This is my LS. So what should be the voltage across the inductor LS? My VL, it should be what? LS multiplied by DI over dt, and this entire voltage for the positive peak, this entire voltage, since this is also short, this entire input voltage, it will appear across the inductance, right?
Yes, sir.
So in that case, what will be my input voltage? Suppose this is my Vm sine omega t. Now, then what should be my current change rate through the inductance? If I want to calculate that one, my d over dt, it would be Vm over Ls multiplied by sine omega t. So as you can see, the change in current through the inductance, or we can say through the diode D1, it will be changing similar to the sine wave. So suppose we are considering it will take from 0 to some time, like we are considering this angle U. So this is the time when both diodes will be short circuited, will be operating for making this current transfer from freewheeling diode to diode D1. So during that portion, if you want to draw the diode current or the inductance current, suppose this is my diode current ID1, then how the diode current will change? According to this equation, this current change will be similar to the sine wave, right? So we can see this diode current will jump to your current ID in similar fashion like the sine wave. And then after a certain period of time, it will reach to its steady state value. Do you understand what I am trying to say here?
Please, sir, could you explain it again?
Yeah. So during this portion, 0 to U, and U is the commutation angle. So here we are saying U is the commutation angle. Commutation angle. So as I am saying, from 0 to U, what is happening here? Both diode D1 and DF both are operating because this inductance doesn't allow this diode D1 to have a total ID current instantaneously. So D1 will take the current, that is load current, in a slope which is similar to the sine wave. So as I am saying, the current that is going through the diode, it will change like a sine wave. And then after a certain point, it will take all the output currents through the diode D1. Do you understand what I am trying to say here?
Yes, sir.
So now what will be the current then for IDF then? IDF. So the way the current through the diode D1 is increasing, as you can see here, since my output current is constant, the way the current will be increasing in diode 1, similar way, the current will be decreasing through the freewheeling diode. So here, as you can see, it is jumping from 0 to D. So the current through the freewheeling diode, what will happen to it? Before that, during this negative half cycle, you can see this diode was operating. So inter ID current was going through this freewheeling diode, and during the commutation process, the current will drop down like a sine wave, and then it will remain zero until this thing happens. So now, during that portion, is there any question regarding so far what we have discussed?
Sir, sir, am I audible?
Yeah, I can hear you.
Sir, এখানে মানে প্রিভিয়াস ডায়াগ্রামের আই ইনের নেগেটিভ মানে পজিটিভ এর জন্য তো একটা কারেন্ট পাচ্ছি, বাট ওয়াই ইজ ইট জিরো ফর নেগেটিভ VIN? Why isn't it's negative IN instead?
Because this current is going through your freewheeling diode. So if the current is going through the freewheeling diode, then the diode is D1 is reverse biased during this portion. And if the diode is reverse biased, will there be any current in the input?
স্যার একটু রিপিট করা যাবে আবার?
During that portion here, the DF is working, right? During the negative half portion.
Yes, sir.
If the DF is working, then DF will work as a short circuit, right?
Yes, sir.
So if the DF is short circuit, then what will happen? This positive terminal, as you can see, this positive terminal, that DF is short circuited, so it will appear here, right?
Yes, sir.
And the negative terminal is here. So the diode, will it be in forward biased or reverse biased?
Okay, so DF will be in forward bias, but D1 will be in reverse bias.
Yeah, so if the D1 is reverse biased, will there be any input current?
Okay. Now I get it. Thank you, sir. No, sir, no current.
Okay, so now, then here you can see the diode D1 takes off all the current ID, and here also the diode DF gives all the load current to D1. So as soon as this diode DF current reaches to 0, then what will happen to DF? It will be turned on or turned off.
Turned on.
Turned off. So now, if I want to draw the output voltage waveform, then during this portion, from here to here, since DF was on, and although it is the current through the diode DF is decreasing, but still it is operating, meaning the output across the output would be 0. So from here to here, although we should have the input waveform something like this, but during this time, my output, it should be 0 because this diode DF is still operating at from 0 to U. And as soon as that current through the diode DF goes to 0, then this diode will operate like it in the reverse biased. And then if the diode is reverse biased, meaning there is no diode operating here, what will happen? What will happen? So now, after that point, if this diode DF is not working, so what will happen to the output voltage?
It will follow that sine wave.
Yeah, the entire input voltage, it will appear across the
Yes.
output.
Yeah.
So after that, after this portion, as you can see, your entire output voltage will be following your input voltage.
এখানে সোর্স ইন্ডাক্টেন্সের কোনো থাকবে না, প্রভাব থাকবে না।
For what?
How will the output voltage follow the input voltage if there is an inductor?
Because when the current reaches its peak value, is there any change in current here?
Okay, the differentiation is 0.
Yeah, so whenever the differentiation is 0, the voltage across the inductor, it would be 0, right?
Yeah, I get it, sir.
Any other question? So now, if I want to go from positive to negative, so here the diode D1 is operating, and now during the negative half cycle, again, this freewheeling diode will come into scenario. But since this inductance is here, will this change of current will be a spike one, or likewise at the starting of the cycle, positive half cycle, the way the current is changing, it will repeat itself in the negative half cycle as well. What do you think?
It has to change gradually.
Right. So in that way, during the negative half cycle, although for the negative half cycle, as you can see, it is going drastically from certain value ID to 0 instantaneously, but when we don't have any inductance, or we are not considering any source inductance, but since we have a source inductance here, so from 0 to U, again that value, this current through the diode D1, it will be drastically going to 0, like the sine wave. And the way it is going to 0 from here to here, then from this part on, this current will linearly increasing, and then it will become ID again during this point. Do you get my point?
Yes, sir.
Anybody, is there any question regarding this? So now, for the ideal case, if we don't consider any source inductance there, what was the average value of this half wave rectifier? Your V naught average was what? 1 over 2 pi. Then it was what? 0 to
I
pi Vm sine omega t
sine.
multiplied by d of omega t, right? And then this value, how much we got? It was Vm over pi, right?
Yes, sir.
Just give me 1 minute. I need to take a call. Okay, so when you have the full waveform, then your output voltage was Vm over pi. So for this waveform, what would be the average value then? Whether it would be same or reduced, or what do you think?
Reduced.
Reduce. So it should be the average value then. It should be, then what should be the average value? Your V naught, in this case, it should be the, for the idealistic case, if we consider this value Vm over pi, so this should be Vm over pi minus the area this much, right? Area divided by 2 pi, right? Do you understand what I did here?
Yes, sir.
So what is this area? This is starting from 0 to u. So what is the area here? What is the equation of this waveform? It should be Vm sine omega t, right? So
Yes.
what should be this area then? This area, this voltage is appearing across the inductance, right? When D1 is short circuited, then what is happening here during this commutation? If you consider this thing, so if I draw this during commutation, the situation was like this, and the inter input voltage, it was appearing across the inductance, right? What we did here, right?
Yes, sir.
So now, if this is my equation, let me write it down like this. So Vm sine omega t, that should be equals to Ls multiplied by di over dt. So now, if I consider this is the equation with respect to t. So if I change this equation with respect to the theta or the omega t, what we can do, we can write it down like Vm sine omega t, that should be equals to Ls multiplied by, if I change it with respect to omega t, a omega will come forward and it would be di over d omega t. Do I need to explain that again? Because I have explained that several times, I think. Do I need to explain that? So suppose your I is Im sin omega t. So can you tell me what should be my di over dt? Im multiplied by omega multiplied by cos omega t, right? What should be my di over d omega t? It should be what? Im cos omega t, right?
Yes, sir.
So this thing, we can write it down like omega multiplied by di over d omega t, right? So now, then if I take the integration on both sides, Vm sin omega t, it is changing from 0 to u. So during the commutation time, if I want to get Vn sin omega t, then it should be equals to omega ls. Then it would be integration di over d omega t. Sorry, we need to add here d of omega t, and you need to multiply here d of omega t. So it will cancel out. So it will be the only the change of current, right? So how the inductance current is changing during the commutation time? It is changing from where to where? From 0 to what was the final value? ID, right? So it is changing from 0 to ID. So from here, what we can write? So from 0 to u, Vm sin omega t, that should be equals to omega ls multiplied by I that have a value of id and 0. So it would be equals to omega ls multiplied by id. So what is this integration? This integration is the area that is under this cross-section curve, right? That should be this curve, this area, right? So if I put this value here as the area, then what we can write? Your V naught, it would be Vm over pi minus your area is omega ls id over 2 pi. So from that one, what we can conclude, if your ls value is getting bigger, then what will happen to the output? Whether it will be increasing or decreasing.
A decrease.
Again, for the same inductance value, if your output current or the load current is higher, then what will happen to the output voltage? It is also decreasing, right?
Yes, sir.
So here we can conclude that if ls is increasing, your V naught average, it will be decreasing. Or if your load current is higher, then for the inductance effect, your output voltage average will be lower as well. Now, do I need to explain that for the full wave rectifier, or now you can realize what is happening there? Okay, so another thing I forget to explain, that sometimes you might be asked to get the value of the commutation angle. So if I continue this integration, then what we can write, my Vm, what is the integration of sine omega t? It should be, here you should have d of omega t. So what would be the integration of sine omega t? It would be minus cos omega t, right? And the higher value, it should be u, and the lower value is 0. And that should be equals to your omega ls id. So now, if you put this value, then it would be Vm minus cos u and then 0. So plus 1, it would be equals to omega ls id. And then we can write what is your Vm. Vm is root 2 multiplied by Vs. Vs the RMS value. So if you multiply RMS value with square root 2, then you will get the maximum value. So 1 minus cos u, that would be equals to omega ls multiplied by id. And then from that one, we can find the commutation angle cos u. It would be equals to 1 minus ls omega id over root 2 Vs. That is the equation for commutation angle. Now tell me, do I need to go through the full wave rectifier circuit considering the inductance effect? If you don't talk, then I will close the class today for today.
It would be better if you explain.
So now for the full wave rectifier circuit, if I consider the idealistic one, suppose we have a full wave rectifier circuit without the source inductance, but we have 4 diodes. This is my V in. This is D1, D2, and then this is D3, this is D4, and then we have a current source. It is your output voltage V0, and this is your source current ID. So this circuit actually can be represented by your input voltage. We are having like this, and then it should have a diode D1 going to the current source ID. And then it is getting back by your diode D2. and it should be connected here. Similar way, for the positive half cycle, it will go through your diode and then it will go through your diode D1. And then while returning back, it will come through D2 and go back to here like this. And now during the negative half cycle, what will happen? The polarities, it will be changing. So this should be negative, this should be positive. So during the negative half cycle, the current will start following through D3 and then it will be going to the node. So from here, actually, for the negative portion also, here, you should have another diode connected to it. That should be your D3. Because during the negative half cycle, the current will go like this. And it should be connected here. And the current will go through D3, and while coming back, for this portion, it should be connected to another diode. That should be your D4. And it should be connected here. Now tell me, do I need to explain the full wave rectifier waveform again, or you know what's happening there? So suppose this is my input voltage. This is my V in. So what would be the rectified output? Rectified output. Something like that, right? And if my load current is a constant one, because this is my I naught, it is a constant one. So during this portion, during the positive half cycle, for this portion, D1 and D2 will be operating, and during the negative portion, D3 and D4 will be operating. Again, D1 and D2 will be operating during this portion, and D3 and D4 will be operating during this portion. So when D1 and D2 is operating, so the current ID1 and ID2 will be the same, and it will appear like the same way, the output current like this. And here we'll have another chunk of current, DC current, through the diode ID1 and ID2. And what will happen to the current ID3 and ID4? During this portion, the load current, it will go through ID3 and ID4. And for the negative half portion also, this will happen the same thing. So this is the current. This is actually your ID. This is also ID, but it is going through ID3 and ID4. So now, let us see what will happen if we do the same thing, but considering the inductance in the circuit. So suppose you have a input voltage V in, and then you have a inductance LS, and then you have 4 diode. This portion is connected here. This is going here and disconnected to the source. That is your plus minus V naught. This current is ID. This is D1. This is D2. This is D3. And this is D4. So now, if I want to draw the input waveform, so the input waveform will be like this. So if I draw this thing, so now during that portion, when if I consider the negative portion also here, so can anybody tell for the positive half cycle which one is tends to operate? D1 and D2 here, then here D3 and D4, again here D1 and D2, and again here D3 and D4. And before that also D3 and D4 should operate in this region, right? Is there any confusion regarding this so far? Now, tell me, so what will happen to your input current then? If I want to, suppose for this portion, D3 and D4 is operating. So D3 and D4 is operating. Let me draw it here. So this way. So suppose we are having the circuit. This is my D1. And here it is connected to D3. D3. Both are connected together. Then we have a current source. And then on the way back, this is D2. It is connected here. And again, D4 is connected here. Okay. So during the negative half cycle, what is happening here? This D3 and D4, it was short circuited, and we don't forget to introduce a inductance here. So D3 and D4, it was operating during the negative half cycle. So we will think that if I draw ID1 and ID2 here, and then again we draw ID3 and ID4 here. So during the negative half cycle, we can think of this current ID this current, the load current, it is coming from D3 and D4. So D3 and D4, they are carrying current ID. And the current is going through in this direction. So this way it is going. So now, as soon as the positive portion of the waveform comes, then what will happen? This diode D1 and D2, it will start operating. It will be short circuited like this. But since you have an inductance here, the inductance will not allow this D1 and D2 to have the entire jump as we did for the half wave rectifier case. So if I consider my delay angle here, this is from 0 to U. So during that portion, what will happen? This diode D3 and D4, it will, from ID, it will drops down to 0 like a sine wave. And then the current through the diode ID1 and ID2, it will be 0, and then it will start increasing and it will reach to your ID value after a certain point when this current through ID3 and ID4, it will drop down to 0. Do you get my point?
Yes, sir.
And during the negative half cycle, what will happen again? It will be 0 until this point. And then it will drop down like a sine wave. And this current will increase like a sine wave. And during the negative half cycle, this current will be ID and this current will be 0. This current will be 0. And the process will repeat itself. Now tell me, as you can see, instead of having a spike from 0 to instantaneously 0 to ID value transition, we'll have the current increase or decrease according to a certain value, and to our calculation, we can say it will be similar to the sine wave. So now, during that transition, when the D1 and D2 operates, what will be the direction of the current through the inductance? Current direction will be the same or different? Do you understand what I am trying to say? So when suppose D3 and D4 was operating, so D3 and D4 was operating, what was the direction of current? The correct direction of current was like this. So the current during the negative half cycle, it is going in that direction, right? And now during the positive half cycle, when the polarity is reversed, in that case, D1 and D2 will be short circuited, and the current through the inductance, it will be like this. So what will be the direction of the current then? In this direction, right? So will there be the same direction of current, or the current direction will be changed? What do you think?
Is same.
So during the positive half cycle, when the current is transitioning from 0 to ID, actually what will happen here is that when the current drops down to 0 and it is increasing from here, so what will happen up to this point? So if I now draw the inductor current, suppose this is my ILS, or you can say this is my I input. So what would be your I input? From this point to this point, that current will be the positive current, that is ID, because we are considering this direction to be the positive one. And then during the transition period from D1, D2, when the current through this D1 and D2 is decreasing and the current through D3 and D4 is increasing, so it will transition from ID to minus ID, because the direction of the current, it will be reversed during the negative half cycle. So it will transit from plus ID to minus ID. And similar way, it will have the current waveform like this. where it will be transit from minus ID to plus ID here, it will be transiting. So now, if you consider when you have a full wave rectifier, what was the, without the source inductance, what was the average value of this waveform? What was the V naught? What was the V naught? It was twice Vm over pi, right? So now, if I want to draw now the output waveform, so this is the during this portion. And again, during this portion. So if I draw the waveform like this, so after this portion, when the commutation is off, your output voltage will be similar to the input voltage. This is my output, and this portion, you will get this waveform like this. But what you will be missing, that is the identified area like this. So now, what would be the output voltage here? Your V naught, it would be twice Vm over pi, and you have two area having equal magnitude. So minus 2 multiplied by area divided by 2 pi. You got my point, right? And what was this area? 0 to u. Previously we said Vm sine omega t. It was Ls multiplied by di over dt. So now, okay, so we made one mistake here. So the output here, it would be minus ID to plus ID, something like this. Not from here. Okay. So now, again, if I write it down, Ls multiplied by omega, then it would be di over d omega t. So now it would be, if I integrate 0 to u, Vm sine omega t multiplied by d of omega t, it would be Ls omega, and then integration of di. But here, during this commutation period from here to here, the current through the inductance is changing from minus ID to plus ID. So we can write it down like minus ID to plus ID. So it would be twice Ls omega multiplied by ID. So this thing actually representing the lost area. So if I put this value here, so what would be my V naught then? V naught would be twice Vm over pi minus 2 multiplied by 2 Ls omega ID over 2 pi. Or we can write it down as 2 Vm over pi minus 4 Ls omega ID over 2 pi. Here also you can see, if you increase the source inductance or the current value, output current value, your output voltage, it will drop. So there is some mathematics in your Ned Mohan's book regarding the commutation angle. So I would request you all to practice that value, that mathematics. And if you have any further question, you might ask me. Otherwise, I will conclude that class today.
Sir, can you hear me?
Yeah, I can hear you.
Sir, can you please scroll up for a bit?
What?
Can you please scroll up?
Yeah.
Sir, are we two পড়ে মানে ফার্স্ট ওয়েভ শেপ এর যে ডায়াগ্রাম ওটাতে Yes, sir. স্যার অ্যাকচুয়ালি আমরা যখন যে কোনো সার্কিটে যখন আমরা বলি যে ইনপুট ভোল্টেজ হচ্ছে যে VIN, তো অটোমেটিক্যালি কি আমরা এটা অ্যাজিউম করে নিই যে ইনপুট কারেন্টও হচ্ছে যে IIN, বিকজ আমরা যখন ফার্স্ট হাফ সাইকেলের জন্য চিন্তা করি তো তখন the input voltage is positive, let's say, with respect to one scenario. আবার হচ্ছে যে তো ওইটার সাথেই হচ্ছে যে কারেন্টটা যেটা যায় সেটা হচ্ছে পজিটিভ। আবার সিমিলারলি যখন নেগেটিভ হাফ সাইকেল যখন নেই তো সেই ক্ষেত্রে কি আমরা এটা বলতে পারি যে আমরা একই সাথে